All right, this is the second lesson of calculus, unit 1.5. We're going to look at piecewise functions and their limits. So to begin, this statement we learned with the last lesson that the limit as x approaches any value exists if and only if the left-hand limit and the right-hand limit agree. And that's kind of what this statement says. It just says the limit as x approaches c of f of x exists if and only if the left-hand limit and the right-hand limit are equal as x approaches c. Now, normally this is really easy to do when you're looking at graphs because you can see the values, but with functions it's a little harder. And we're going to look at piecewise functions and see if the limit exists. Now, if you could graph both of these equations, you would just check. But without that, let's see if we can use some algebra. So starting off with the first question, it does give us f, g, and h. So be careful when we're talking about f of x, we're talking about this function. When we talk about g of x, we're talking about this function. And then, of course, h of x is this function. So each of these requires a little bit of separate algebra. Now, I will say this first one says the limit as you approach 0 from the left of f of x. So what that means is that we are less than 0 if we are approaching from the left. Because here's 0. If you're approaching from the left of 0, you're going to be less than 0. So if we come up here to our piecewise, left of 0 is going to be this part here. It's going to be when it's less than 0. So we're going to use this equation to evaluate this limit. So what we're going to do is just substitute 0 into our equation. And that's going to equal -3. And again, we don't care. Remember, with limits, we don't care what actually happens at the value. We just care as we get close to the value. So we're going to plug in 0 here, even though it says less than 0, not equal to. Again, we're just checking the value at 0. Okay, now we're going to do the same thing, but from the right. And if you are going from the right of 0, that means your x values over here are bigger than 0. So that's going to be this portion here that's to the right. So now we're going to plug in 0 into here and check to see if it equals this -3. So plugging in 0, this is going to give us 0 plus, and then anything to the 0 power is 1. So this equals 1. Now notice our left-hand limit and right-hand limit don't exist. So if we go over here to the next and says, hey, what happens if we just approach 0? Well, you'd have to check the left-hand limit, which is equal to -3, and the right-hand limit, which equals 1. And so you will say that this does not exist. And if it asks you why, you can argue that the left-hand limit does not equal the right-hand limit. And there you go. That would be your explanation if it asked you for a rationale. Part D says, what is the value at 0? Well, the value at 0 is this one, so it would be the same as this. Because this is when it's equal to 0, so we use this equation. But we've already plugged everything in here. So this is just equal to 1. So our limit as we approach 0 did not exist for f. Let's check for g. So for g, now notice, for g it just asks what's the limit as you approach 1. G is this equation. So we need to check the left and right hand limit. So let me highlight, right? This will be the left hand limit. And the right-hand limit will be this one right here. We got to check to see if these match. Okay, so we are going to, again, plug in 1 into here. That's going to give us 4 minus 1, which is 3. So my left-hand limit is 3. Now let's plug in the right-hand limit by using this equation here. Again, to the right means that you're going to be bigger than your value. In this case, it would be 1 right here. But going to the right means you're bigger than 1, so we use this equation. And in this case, we're going to get 5 minus 2, which is 3. And so we did a good job. This limit is 3 in total because the left-hand limit was 3 and the right-hand limit was 3. So the limit here is 3. And then part F says, what is the actual value at 1? It is 5. Okay, so if we look at H, this one says, what happens as we approach it? Negative 3. So basically, we're going to use this equation when we're not equal to negative 3, but use this equation when we are equal to negative 3. Right? So we're going to do this equation. Let's rewrite it down here. Okay, so from pre-calc, we have learned that when you see polynomials in the top and bottom in this rational equation, we need to factor the top. So we need to factor x squared minus 9. Again, if you do x squared minus, and you're like, okay, what multiplies to negative 9 and adds to 0, because remember, there's no x term, we're going to get that this is 3 and negative 3. So this factors to x plus 3, x minus 3. And on the bottom here, we have to figure out what multiplies to 12. And then adds to 7. That's going to be 4 and 3. So this will be x plus 4, x plus 3. We have these cancel out. So we get x minus 3, x plus 4. Now, we're going to use this same equation for the left and right-hand limits. Just because when we are less than 3, we use this. Less than negative 3, we use this. When we're greater than negative 3, we use this. We only use this bottom equation when we're equal to negative 3. So we're going to use this for both our left and right-hand limits, which means we are just going to sub in x equals negative 3. This is going to be a shortcut notation you see later. We're just going to use it now. It's a calculus way of saying substitute into our equation. So we're going to plug in negative 3 in top and bottom. And then we're going to get that this is equal to negative 6 over 1, which is just equal to negative 6. And that is our limit. And then over here, what happens when what's the value at negative 3? Well, it's 0. So there you go. We had function f that the limit did not work, g, the limit worked, and h, function h, the limit worked. All right, example 2, you will see these types of equations. These are usually on multiple choice, maybe as a part of a free response. But it basically says, here's the piecewise function where c is some constant. Find c such that the limit exists. So remember, we are approaching x equals 2, right? So that means my right-hand limit needs to equal my left-hand limit as I approach 2. So as I approach 2 from the right and I approach 2 from the left, those values have to be the same. Well, look here at our piecewise function. This is when it's less than 0. This equation is when we're from 0 to 2, and this is when we're bigger than 2. So we need these parts to figure out our answer. Now again, I drew a graph right here. So when we are moving to the right of 2, that means we are bigger than 2, which is this equation here. And then I will highlight this in yellow. And then in orange, we're going to use this equation. This is the left-hand limit. And again, visually, because when we're from the left of 2, that means all of these values here are less than 2, which is this equation here. And we're going to plug in 1. I'm sorry, 2. We're going to plug in 2. Because again, so the 2 goes here, and the 2 goes here. And then we solve our equation. So this is going to be 2 plus 1 squared minus 5 equals 7 minus 2c. Now let's go over here and do some algebra. So again, this will be 3. 2 plus 1 is 3 squared, which is 9. We have 9 minus 5 equals 7 minus 2c. This equals 4. And then we're going to subtract 7 from each side. So that will be, 4 I said, minus 7 is negative 3. Equals negative 2c. And if you divide by negative 2, you get 1 1/2 is equal to c. So if c is equal to 3/2, this function will have a limit at 2. Means the left-hand limit and the right-hand limit will be the same. All right, so this is a special case. This case pops up a lot. I've seen it on multiple choice questions. They focus on this. It pops up when we do derivatives. There's so many different little avenues this little detail pops up. So we're just going to look at the case right now and try to get it out of the way. All right, so it's really the graph here. This is what we want to find. And if you look, it's really not that hard. Here is the graph. Basically, it equals 1 as you go to the right, and it equals negative 1 as you go to the left. And that's really the gist of it. But let me show you where this comes from. So this is the graph of the absolute value of x. This graph right here in dash marks that I did. Now, this piece right here of the graph is defined by negative x. Right? The equation that describes this is negative x. Because again, right here, this point is negative 1, 1. So do you notice how the x and the y are opposites of each other? This point over here, oh, this graph is not done properly. There we go, sorry. Oh. There we go. This graph right here is negative 3, 3. So notice how the x and the y are opposites. One is 3, one is negative, and that's what this says. Now, this portion of the graph is defined by positive x. You can use positive x to write the equation to this part of the graph. Again, this point is 1, 1. Notice how your x and y are the same. And if it helps, this is equal to y. I guess that makes more sense, right? This value is negative 3, 3. The x and y are opposites. That's what that says. This one, the x's and y are the same. This is 1, 1. This point is 2, 2, 3, 3, so on and so forth. So you can write absolute value of x as a piecewise function. You can say that it's negative x if x is less than 0, and it's positive x if x is bigger than 0. Because that's what absolute value is. It is a piecewise function. I don't remember if that is taught in pre-calc. Maybe it is, maybe it isn't. Okay, but anyway, so that is the absolute value of x. But, Busby, we're supposed to be doing the absolute value of x divided by x. Okay, whatever. All you have to do to modify is divide this by x, and by x, like here. Because now this graph is the same, and I just completed it here. Now look what happens. This part of the graph turns into -1. So you could say, or it equals -1 if x is less than 0. And this part of the graph equals 1. And this is the big key right here. So let me rewrite this formally. And there you go. That's where it comes from. So the graph, and they're both open dots, goes this way and this way. Oops, let's actually draw it properly. And so there is the graph of absolute value of x over x. And just to show you again, that's what we got here. That's where everything comes from. But you need to know the reason why, because sometimes I ask questions in a way where you have to understand what's going on. Now, all of this stuff, graph the following. All right, so what about this? Well, from your Math 3, your pre-calc, we know that this is going to be 2 right. We move this 2 to the right. It's always opposite from what we say. So if you have a graph that looks like this, and normally if it goes this way and this way, you're just going to move all of that 2 to the right. So it's going to start here. Again, this is open dot. It's going to go that and that way. Again, and this is at 1 and -1. Okay, so this next one, this is going to be +4, but anything in a parentheses is backwards. So this is going to be left 4. And then this is going to be a vertical stretch by 3. Think of it kind of like this. So again, this will still be 1 and -1, but then it's going to be times 3, which is going to kind of take it to -3 and 3. But I'm actually just going to cut the graph on this one. It's too... I'll just draw these manually. Okay, so we're going to draw left 4. So this is going to be 1, 2, 3, 4. And then we're going to go up to 3 and -3 instead. And we're going to go to the right and to the left. Again, this is at 3 instead of 1 because you multiply everything by 3. So imagine all of this getting multiplied by 3. If there was a 3 out here, the 3 would go up there and there. Plus, we have a movement left by 4. Right, so you're moving this left 4 and then moving it up to 3. So this one, it doesn't matter if the absolute value is on the bottom. It's just trying to trick you. This is going to be right 3. But notice how there's like a 1 here. So this is going to be a vertical shrink by 1/4. So this is 1 and -1. The first thing we're going to do is move everything over 3. So to here. Because again, we're moving right 3. But instead of getting multiplied by 4, we're multiplying this by 1/4. So this is going to be -1/4 and 1/4. Let me just erase that just so we know. And so there is my other function. And there you go. So as long as you can manipulate that and recognize the graph, you're good. This is a special case that's going to pop up. And here is your second AP question. It's from the 2014 exam. I know most of you probably weren't born around then. I feel old. But let's look at the graph real quick. So this is going to be to the right 3. 1, 2, 3. So we're going to go up like this and down like this. So this question says, as we approach 3 from the left, which means as we go this way, we're going to be at -1. So this is getting closer and closer to -1, and there is your answer. Take care. Enjoy.